discontinuous mode quickly last time. I just want to draw a few waveforms away from this set of equations. So just as a review for the buck converter, okay? For the buck converter, I have my input source like this, and I have my MOSFET, and I have a diode, capacitor, and resistor. When I refer to discontinuous mode, what am I referring to? What is discontinuous?
Current, output current.
Inductor current, always. It's when I'm referring to discontinuous mode, I'm always referring to inductor current, right? Inductor current is discontinuous. So let's see, in continuous mode, what were the waveforms looking like? So what was the inductor voltage equal to in continuous mode? When the switch was on, what was the inductor voltage? The switch was on. This is on. This is off. What's VL when the switch is on?
Vin minus V out.
Vin minus V out, sure. So, right, when the switch is on, the diode is off, so this terminal is connected to this side of the inductor, and the other side of the inductor is connected to my V out, right? So that's Vin minus V out. How about when the switch is off?
Minus V out.
So this is off, this is 0, then it's minus V out that's across the inductor, so it's minus V out. And this was for the whole switching period, right? And this area always equals this area as long as I have an inductor operating in steady state. All our converters are operating in steady state, right? All our converters, so any capacitor current will have an average value of 0. Any inductor voltage will have an average value of 0 as long as I'm operating in steady state. But in continuous mode, there's another thing that is satisfied, is that I have voltage or current across the inductor for the whole switching period, right? This is in continuous mode. What does the corresponding inductor current look like if this is the inductor voltage? It starts from some initial condition and then rises since I have a positive voltage across the inductor, and then falls down since I have a negative voltage across the inductor, and this is I minimum, and this is I maximum, and this was my delta I spec that you've designed for and you've selected your inductor for. Okay? So what's happening now? This delta I has an average value of, sorry, this current, the inductor current here has an average value of what? Average value. What's the average value of this inductor current? It also happens. It happens to be the average value of the load current. It's the average value of load current. Since this capacitor have an average value of current equal to 0, so average inductor current will be equal to average load current in this case, right? Yes. So if I decrease the load current, what happens?
The average goes down.
The average will go down, right? So this average will go down. Does the ripple change? How did I design my ripple? Ripple was dependent on my switching frequency and my choice of inductor value, right? So ripple did not change. So ripple will not change, but my average value of inductor current is going down. If this goes down, at some point, this point here, this minimum value will reach 0, right? I keep pushing it down further, I keep pushing the average value down further, I will end up at some point with maybe something that, yes sir?
If we drop the current, doesn't that mean we increase the resistance? But then,
Yeah.
by then, we decrease the ripple.
Decreased, why would that?
How do we make the current?
Again, how do you select inductor? Inductor equal to delta lambda over delta I spec, right? So this delta lambda is the area under this curve. Does this change if I change the resistance? The voltage does not change. I will always have Vin minus V out for a specific Vin and a specific V out, right? Right? Fixed Vin, fixed V out. This waveform will never change. This waveform, the voltage across it will never change. So the area here will never change, right? So since this area is not changing, then the ripple will remain the same if I, basically have selected an inductor based on this ripple current, right? So the ripple will remain the same, and I will end up with this is my current in this case. Let's say it will start at 0, but I've dropped it to I dropped the average value considerably so that I'm crossing here, right? And this was my original waveform. Like this, let's say this was my original waveform. Right? This was the original wave. This was my original waveform that I had here. The switching period is from here to here. Right? Now I changed that. I mean, I kept dropping the average value until the minimum value of inductor current reached below 0. Right? So there's no such thing as below 0 because it cannot go negative. Can the inductor current go negative? Inductor current will not go negative. The diode cannot go through here, and it cannot go through the MOSFET. Cannot. Right? So inductor current will not be able to go backwards. So what happens is as soon as it gets to 0, there's no more energy stored in the inductor, right? You have energy stored in the inductor. What are you doing? You're putting a negative voltage across that inductor. What is that negative voltage doing? It's taking the energy out of the inductor until at some point you have no energy in the inductor because it's equal to half Li squared. There's no Li anymore. There's no current in the, or IL, sorry, anymore, right? It's 0. So this happens at some point here. This repeats now every switching period. This whole cycle where the inductor has current rising and then the inductor current is falling, right? This was happening when? When the switch was on. This was happening when the switch was on, right? And then I put a negative voltage here across the inductor when the switch is off, right? Depending on my value of load resistance, this current will fall down quicker or slower, depending on the value of resistance, right? Since this value of resistance is going to be controlling the average value of my original waveform that I had here, right? If I bring this down, I can make the average here, right? If I make the average here and the ripple is the same, then then the waveform looks something like this, right? So this is just the average being brought down. So I brought it down to a point where I have places in my switching period where there is 0 current. And that's called discontinuous mode, right? But there's something that will never change. That the area here always equals the area here since I have an inductor operating in steady state. So I can be operating in discontinuous mode in steady state, right? This continuous mode is a steady state condition. It's not a transient condition, right? The converter can be operating in continuous mode, like here, or discontinuous mode, like here. But they're both steady state conditions of operation for the converter. The load is steady state at a very low load, right? So, and same with the capacitor current. So the idea is, the equation that we talked about last time was the volt-second balance. So we used the volt-second balance, or the area under this curve. We equated the area under this curve with the area under this curve for the inductor. This was equal to this, or this plus this was equal to 0. So that's what we did here. This plus this equal to 0. This, the area Vs minus V input minus V output. This is the voltage across the inductor when the switch is on, plus the other area which happens to be negative. It's the which is negative V output times the duty cycle D1 that we don't know what its value is, multiplied by the switching period, right? So this is called volt-second balance. So from the volt-second balance, we found the relationship. Then in the textbook, there was a derivation for this D1 duty ratio that we don't know, part of the switching period that we don't know about, in terms of everything else that we know about, right? So I just wanted to stress again on the discontinuous mode. Everybody's okay? If you have a converter that runs all the time, but not necessarily has a load on it, right? Which would be a more efficient solution, actually? continuous mode or discontinuous mode. Efficiency, from an efficiency perspective, for the same average value of current required, right? One converter in continuous mode will have what? Will require that current is always continuous, that this average value of current is always flowing through my inductor. And in the other case, it's only for a short period of time. So there's no conduction losses for a part of the cycle, there is switching losses, but there is no conduction losses for a part of the cycle, and there's no inductor current flowing for part of the cycle. So for the same value of load that you may require at the output, having a discontinuous mode power supply may be more efficient. But you may also have a bigger size inductor for the same ripple. So if you have the same ripple, let's go back to the for the same value of ripple current. This is ripple. This is ripple. No, for the same value of ripple current, inductor size will not change. Sorry. But just maybe a more efficient solution for a specific average value of current. If this is producing the same average value of current as this converter, here I have continuous current in the inductor, here I don't. Right? So let's say you have a computer power supply that is you want to control only in continuous mode. Then you will require to have a minimum load on the converter all the time. Can you imagine if you're operating this converter only in continuous mode? That means you have to have a minimum value of load on the converter all the time present here. In discontinuous mode, if your controller can operate in continuous and discontinuous mode, you can remove the load, and the converter will operate in discontinuous, bring the average current down, operate in discontinuous mode without a minimum limit all the time. I don't know if I'm making sense. I'm just saying, in continuous mode, you always have to have a load connected, right? In discontinuous mode, I can remove the load. No, but from control perspective, you may not like the performance of the discontinuous mode power supply from a control perspective. Like the transient response, I don't know. We will not study the controller response of the discontinuous mode. We only study because if we in discontinuous mode, we will have to use nonlinear control, not 420 type material. So it's a completely different way of controlling the converter here. So it's I think it's a control issue. We would have to do a more deeper evaluation, but if here we're introducing continuous mode and discontinuous mode of operation of the converters. I can satisfy a load here while operating in continuous or discontinuous mode. Does not matter. So, and both for the buck and the boost converter, we went through them last time, and we saw that there's always this D1 variable that will be calculated in terms of other parameters in the circuit, and the derivation for that, again, it's in the textbook. I'm not expecting to know the derivation. The idea is we do volt-second balance across the inductor. We always have a D1 in terms of the parameters of the circuit that we will take and plug into the volt-second balance equation. Simple. Okay? So, the last thing in this chapter is what we've been talking about before. I mentioned before is the idea: how do you link this to 420? Right? How do you link this to what you guys are studying in 420? If you, from your homework or from the labs, when you looked at the waveforms, you saw the inductor current ripple waveform, and you know that maybe you maybe also plotted or looked at on the oscilloscope, or the switching, the voltage, the gate of the switch waveform, or the voltage across the switch waveform. These are all waveforms you saw, right? And this is called a switched model of the power converter. So from a simulation perspective, this is fine and everything, and you can simulate a switch model with no problem. Yeah. But if your target is to develop a controller, right? Then this switch model requires a lot of calculations that you don't require. So from a linear control perspective, linear control would not talk about ripple. Like it will not be affected, the control or the ripple here will not be affected by the gain that you utilize in your linear controller. It will not be affected by that. The ripple here will be purely controlled by switching frequency and the value of the inductance that you've chosen. Purely, it's L is equal to delta lambda over delta I. You've chosen a certain L based on a certain value of input voltage and output voltage and switching frequency. That's it. The ripple will not change. So why bother yourself with a very detailed switched model in your simulation process when you can go to an easier model? That's one reason we would try to come up with a model for the circuit. The other reason we try to come up with a model for the circuit is you want to control this device, this power converter. The only parameter that you can control is what? No. After everything is set, you've chosen your switching frequency, you've designed your converter, everything. We've done everything we've done. We chose our diode, chose our MOSFET, chose our inductance, chose our capacitance. Everything is done. Huh? No, load is something that can change. Load is something that can change. Load is something that can change, right? So if load is something that can change, you want to make sure that anytime you change the load, the power converter maintains the same voltage at the output, right? That you would like that to happen, yeah. So how do you model any source? Any source, yeah, you will utilize feedback. But typically any model of any source, in reality, a battery, for example, is modeled as well. Ideal voltage source with a resistance in series. This is our R internal, right? So a power converter is a source. A power converter is a source. If you keep pulling more current, this is a power converter. And this is a load resistance. Right? If you keep pulling more current out of this power converter, what will happen to the voltage here? If you don't change the duty ratio, right? Let's say you have a power converter with a fixed duty ratio, right? This power converter, remember, it has an inductor with a resistor in series, right? This resistance in series. It also has a switch with a power loss, with a voltage drop across it, right? It also has a capacitor with an ESR. So all of these things I'm modeling with are internal. So any voltage source, any synchronous machine, a battery, a power converter, any device, any voltage source can be modeled, and in power systems. In 459, how are we modeling synchronous machines in power systems?
Inductors.
A voltage source, ideal voltage source, with a reactance in series. Because there it's AC, so we have to include the reactance. We can put a resistance as well, but here it's DC, right? So we're operating with DC, so there's no such thing as reactance here. So it's only resistance here. But any voltage source can be modeled as an ideal voltage source and theoretically an impedance in series. Let me not say resistance. It's an impedance in series. If we have AC, then this is an RL impedance. If it's a DC circuit, I don't care about L anymore. I just talk about internal resistance. Okay? So any source looks like this. If I increase the current being drawn from the load, there will be a higher voltage drop here. So the output voltage that the load is seeing will drop. Do you agree? Yes? And this is called voltage regulation. This is called voltage. This is called voltage regulation. Ideally, you want the converter to do this. This is V output, and this is load current. Right? If you keep increasing load current, there will be a higher drop across this internal resistance. The voltage of the output will drop. Okay, so do you allow that? You should not allow that. The load, you want to make sure that your load is fed properly. If your load specs don't allow that, then you have to do something about it. What do you do? Change the duty cycle. Think of this as a power supply. If it drops here, okay, you will increase the voltage here at the input a little bit. right? So this is corresponding to controlling duty cycle in a power converter, right? So your only parameter to input is duty cycle. It's the only thing you control because we only have one switch here. We will look at other converters in chapter 8 with more than one switch, but let's say for now we only have one switch and one diode. So we only can control diode D. And so this is my input, right? Dr. Hazm transfer function is equal to what? Output over input, right? It's the transfer. So output is what? Let's say here it's the output of S over D, right? So you should be, how do you come up with, make this circuit look like something that you can come up with a transfer function for, right? Can you do that with a circuit with a switch? No, you cannot. So that's where this switch model will not work for what we are trying to achieve. Now we're trying to figure out, how do I change duty cycle? Do I change it very fast? Do I change it very slow? How do I change it? Because I have my same input voltage and I require my same output voltage. So theoretically speaking, the voltage transfer equation said I only have a single duty cycle to satisfy that, right? But this voltage transfer equation was assuming everything was lossless. Everything was lossless, right? Which is not true. In reality, there are losses for the inductor, the capacitor, the switches, everything has losses. So because everything has losses, then we saw this voltage regulation curve come up. How do you deal with that? You have to change duty cycle. How do you change duty cycle? Do you change it very fast? Change it very slow? It will depend on your load, obviously. If your load is a memory, or your load is a processor, processors are operating at gigahertz speed, right? You buy a 3.5 or 3.2 gigahertz processor. What does that mean? It means that the instructions inside are happening at the speed of 3.2 gigahertz. Each instruction is happening at that speed, which means that the load is changing. Well, instruction is what? You have different gates inside the processor, which are basically a bunch of MOSFETs. These devices are switching on and off, basically changing the load. Right? So they are fed by power supply, and the load is changing at 3 gigahertz. What does that mean? It means that if I'm going to feed this power supply, I need to make sure that the transient response, if I'm going to feed this memory chip or this processor, I need to make sure that my power supply, the step down converter or the step up converter, actually it's a step down converter in most cases, because typically your processors now are like 1.8 or 1.3 volt, right? And you're putting in what? 12 volt or whatever your power supply. Look at your adapter. It will probably be 12 volt or 9 volts or whatever. So you will have a few buck converters in the power supply, bringing down the voltage from 10 volts or 12 volts all the way down to 1.3 volts. Right? So you bring it down to 1.3 volt, but you have to make sure that this 1.3 volt, you're controlling it such that the voltage regulation is very tight. You're already at 1.3 volts. Can you allow for voltage to change by 0.3, 0.4? You probably can't, right? If you're at 1,000 volts, you can allow for 3, 4, 10, 20 volts change in voltage, no problem, right? But when you're at 1 volt, you probably cannot allow for that, right? So your power supply has to be as much faster than your load. Your load requires changes in your load is changing at 100 times a second. Your power supply has to be able to respond at 1,000 times a second, right? The load tries to change, no problem. I will change it as faster than the load, right? So that's where the link to 420 comes into play. But we have to figure out how to convert this circuit into something that looks like 420. And the way we would do that is the following. So let's say take our buck converter, for example. Do you see the objective what we're trying to do? Okay. So this would be the real bonus. Last time was not bonus. Last time is something that I expect you to know. Sorry. This would be the real bonus, because I'm not going to spend too much time on it. I'm just going to spend time, and then I will tell you what the bonus is. Last time I was confused.
So the design thing
The design problem is something you need to know. Yeah.
for the exam or in general?
I think you should know it for the exam.
Okay.
I think you should know it for the exam.
Okay.
Okay. But this will be bonus. This will be bonus. Because this I will not teach. I will just teach you a bit, and then I want you to relate to 420. Okay? So this is the input, this is the output. and blah blah blah. Okay, so now I want to come. This is something you do not know how to deal with in 420, right? In 420, you can deal with voltage sources, independent and dependent, and then L's and C's. Correct? No problem. This is something you cannot deal with. So there's a mechanism that we will go about. But before doing the mechanism, let me draw some of the waveforms. Okay? Let me draw the gate voltage. So V gate will be the control signal here. The gate voltage will be something that looks like this, right? So this is the switch gate waveform. Switch on, switch off, switch on, switch off, right? And then this, I want to draw the diode voltage. What does the diode voltage look like?
It's the opposite.
Diode. This is switch on. If the switch is on, the diode is off, which means it has voltage across it. That voltage is equal to Vin in this case for the buck converter, yes. Right. So this is Vin. What is the average value of this waveform? Exactly, it's Vin times D, and then I'll just call this, instead of Vin, I'll call this VAP. I'll tell you why I call it VAP. Okay, and then now let's look at the switch current waveform. What does the switch current waveform look like? It's not the inductor current in full. It's part of the inductor current, right? So when the switch is on, there is current in the switch, right? And then it's zero. When the switch is on, there is current in the switch, and then it's zero. And if we assume that the ripple is small for now, then what is the average value of this current? Exactly, it's the inductor current. It's this peak value of inductor current, which we call this I, for example. Yeah, let's call it IC for now. And then this average value is D times IC. We agree? IC here is this peak value of this current. Okay, so if that's the case, let me propose to do this. Let me propose to, this is my V input. And then I will have a terminal here, and a terminal here, and a terminal here. I'll call this active, I'll call this passive, I'll call this the common terminal. Okay? So active because it's next to the switch. Passive, it's next to the diode. Common, it's the common point between the switch and the diode. Okay? So if I do that, the argument is the following. I can replace the switch with this current source. I'll put two dependent sources. I'll always remove the switch and the diode. I'll put dependent sources. But let's see how we come up with the values of these dependent sources. Okay, this is my active, passive, and common. So switch has average current flowing through it equal to D times IC. So we will, every time we see an active terminal, we will put a current source with a value of D times IC, where IC is actually this current here, right? It happens to be also, I mean, same, I can call it D times the peak value. The peak value here happens to also be in the same direction as the inductor current, so I can call this IC. So if this is IC, this is D times IC, and this is the diode. A diode has a voltage, average voltage across it equals to D times Vin, which is also D times, this is Vin. I call this point A and this is P. So VAP happens to be equal to Vn. right? So that's why this is the VAP, right? So if this is the case, right, can you now take this circuit for any L and C value and come up with a relationship between V output and duty ratio? From 420 material, you should be able to do that, right? Yes? Okay, so that's what I want you to come up with for the bonus.
During the exam?
Huh?
During the exam or now and then give
No, you can do that for homework.
Yeah, please.
You can do this at home, right?
Find the transfer function.
Yeah, find the transfer function. Find out what this transfer function equals for the buck, the boost, and the buck boost converter. No. This is a take home. This
So
is,
then between V and V out.
there's no V out. I mean, there's no. It's not between. Your input is the duty ratio, right? Your input has to be duty ratio, right? And your output is the output voltage. Your output can be if you're charging a battery. If you're charging a battery, what does your output? What will your output be if you're charging a battery? Batteries like to be charged with a constant current. So if you're charging a battery case, it's IL to duty ratio. That will be the transfer function of interest. Right? So depending on your application, your transfer function is either going to be controlling the output voltage or average output current. Because here you're controlling the average output current in this case. Right? So for your bonus, I want you to come up with a transfer function and plot the transfer function. You plot it in, have you used Simulink in 420 to plot transfer functions?
Yeah.
Okay, so that's good. So this is coinciding with what you're doing now in 420.
Okay, so you want to find VO over D for
Yeah, do it only for the output voltage. Don't worry about the current. If you want to do it for current, it's fine too.
extra points for current or no?
That's fine if you do it for current.
Wait, I mean, how many points are we getting overall for?
2%,
3%?
2%, 2 or 3%.
5 is good.
No,
It's
2
a
or
nice
3%,
number.
2 or 3%, 2 or 3%.
3%
3%.
to our overall grade.
Yes. But please do it individually. Okay?
Yeah.
Honestly. Yeah.
So, but yeah, you want to do the exam or
No. This is take home. Like do this,
When do you want to buy?
do this, and bring it when you come for the exam. Is that okay?
You want to for the
So Wednesday, you bring it back Wednesday, next week Wednesday. So we
Okay.
have a week to do this. Yeah. For the buck, the boost, and the buck boost. But please, individual work. I trust you. The 3. Yeah. 1%, 1%. Okay.
Can I just double
But
check?
do you see the relationship now between this course now and 420, right? And it depends on the idea of voltage regulation. The idea of because we have voltage regulation, I have to change duty cycle. How do I change duty cycle? I change duty cycle by coming up with a transfer function. This transfer function, you will put a value of L and C, and you will see that if you increase the value of C, you will see that the dynamic response is a lot slower. You can play with the value of C now. Put this for any value of L and C. And when you simulate the transfer function, you have to put values, right? Come up with values and use some values in your textbook, that's good because then you can never be the same. Everybody chooses their own different value of L and C, and maybe compare a few values, and you will see that your choice of L and C, which affect your current ripple and your voltage ripple, is also affecting your dynamic response. Right? So do that. So this is for the buck converter. So now let's look at the boost converter. We'll also come up with very similar thing for the boost converter. Yes, ma'am.
Just checking. So 3% for the VO over D. Anything extra for IL over D?
Yes, I'll give you something else.
Okay.
Just do it, and
Okay.
I don't know. Just do it, and I'll
Okay.
consider. Let's see how nice you do your job.
Okay.
But I mean, for me, the more important thing is that you understand the value of everything we did now, and then how it links to 420, right? That's the whole objective of all of it. Because before, I used to also spend a lot of time doing 420 material, taking this and actually building the controller for the power supply. It was too much for the course, and I could not finish some other stuff. So that's why, you could do this based on your 420 knowledge, and I keep it as bonus. Okay? So let's do the boost converter. So the boost converter looks like the following. So I have my input voltage, and it's my inductor, my switch, my diode, my output voltage, okay. what did we say? The point, the terminal next to the switch is the active. The terminal next to the diode is the passive. And this one is my common point. But the polarities are a bit confusing because the polarities here are going to be flipped, all of them. The polarity in the books, I have to assume that the polarity in the buck converter was the positive polarity, the polarity for the active, passive, and common. And we'll see what I mean here by polarity. So anyway, so if we look at the waveforms, go through the waveforms very quickly again for this. Again, if I put my gate, this is my switch gating waveforms, and then I will draw my, again, we know that this is going to look like what? I'm going to take this and then keep my inductor, and then I will replace my MOSFET with a dependent source, and I will replace my diode with a dependent source. And I can, just memorize or look at what they have, but I prefer to derive it, but I will show you what they have so that we can just plug it in. So here, next to the active, if you go to the textbook, you will see that next to the active will be the current source. Okay? Right? Next to the active node is the current source. Next to the passive node will be the voltage source. Okay? Let's go back and put that here. So this will be my, next to the active is my current source. This is my active terminal. And next to the passive is my voltage source. So the voltage source is D times VAP, and this is D times IC. Okay? But please note that IC here was coming out of the node, right? Out of node C. How about the way we're drawing it? Current is actually coming, inductor current is coming into the node, right? So if I say this is D times IC and this is IC, then this is wrong, right? Then I would have to flip this, right? You see what I'm saying? Because again, the polarity is based on this. IC is coming out of node C, and D times IC is in the same direction here, right? So we will see that it's flipped here. So anyway, so now, and it makes sense, right? Because actually, where is this current flowing? This is inductor current, right? Where is it going to flow? It's going to flow into here, and then into here, right? So this actually has to be flipped. So if I prefer to draw it maybe like this, and write this is D times IL, right? This is my inductor current instead of just IC, or let me call the inductor current IL, and the current here IC, right? This is D times IC. This is part of the current that's flowing out of node C. This happens to be the opposite direction as IL, so I know its value. I know its value is DIL, so I can put that here. Does it make sense? Okay. And then this is D times VAP. We'll see what this will be equal to as well here. So now let's see. So this is the gate voltage. How about the switch voltage? Switch voltage. Switch voltage first. Let's do switch voltage. Switch voltage. When it's on, it's 0. When it's off, it's V out, right? Yes? When it's off, it's V out. On is 0, off is V out. This is switch voltage. What is the average value of the switch voltage? Exactly. It's average value here is 1 minus D times 1 minus D times V out. How about the diode voltage? Diode voltage here is interesting to us. It's the opposite of it, right? Yeah, remember, if the switch is on, diode is off, right? So this is, it's the opposite of it, and it has also a peak value of V output, and its average value is D times V output. And let's note here, V output is here, right? This is my V output. This is V output. What is the relationship between V output and VAP? Negative of each other, right? So I just want to note here that D times V output is also equal to minus D times VAP. Okay, so that's something to note, which is also like, if I want to draw this also a different way, I can draw this as, change the polarity here, flip the polarity, and write it as D times V output, right? If I flip the polarity, this was drawn a different way. Because this is, again, I have to follow a notation. This original one was the notation. And then I can redraw the circuit. Let me redraw the circuit here. I'll redraw the circuit. After we have an understanding of how we derived the circuit, minus here and plus here. Right? This is D times the output, and this is D times IL. Okay, so this is D times V output. How about so this is, we're okay with this voltage source being D times V output, or in a flip polarity D times V output, or in a flip polarity D times VAP. We're okay with this, and we see that it's coming from the fact that VAP is the minus V output. Okay, and then let's draw also the switch current. Switch current, when the switch is on, there will be current, and this will have an average value. Same. It's equal to D times IL, which is the opposite of D times IC, right? If IC is the current that's flowing here. We're okay with this? So now, does all of this make sense or not? I mean, this may be a little confusing, but let's see if it boils down to the same thing that we've been deriving before, okay? At steady state, what does the inductor look like? Short circuit, right? Steady state, inductor is short circuit. Right? This, okay, let's go back one step. This, you can go back and find the transfer function, correct? You will do that for a bonus. And this transfer function is not steady state, it's steady state and dynamic response. The transfer function gives you the time domain response of the circuit, right? But if I want a steady state solution, it should bring us back to what we derived initially, right? The voltage transfer equation. For the boost converter, what was the voltage transfer equation? V output was equal to what? V input over 1 minus D, right? This was the steady state derivation that we assumed before. This will give you your dynamic response based on your 420 understanding or 420 material. I want to confirm that this is correct. How do I confirm that this is correct? I can solve this in steady state. In 420 or in 214, you solve circuits with L's and C's in steady state. If I solve this circuit in steady state, it will look like what? My input voltage, right? And then inductor is a short circuit, right? And then I have my current source, that's fine. And then I have my voltage source, minus plus D times V output. And then capacitor is an open circuit, right? And then I have my output voltage here across my resistor R, right? This is my V output here. So what is V output equal to? Circuit's problem, right? It's V input plus D times V output, right? This is the loop here, right? V output is equal to V input plus D times V output, which if you solve, you bring the D on one side, so it's V output 1 minus D equals V input. You end up with this. You end up, bring this 1 minus D to the bottom here. You end up V output is equal to V input over 1 minus D. V output is equal to V input over 1 minus D. Right? You see the magic? So, this is like 214 to 420, all in one slide. Right, but this is no, really, this is the whole, this is now putting everything together, right? This is you designing on a simple, of course you can have very complicated converters, but this is a simple converter, but you went all the way from your steady state analysis to switch model to dynamic transfer function to steady state again to confirm that you're doing everything correctly, right? Then in 420 you will put this on steroids, right? You will improve the dynamic response by changing the controller, for example. But at the end of the day, change controller, don't change controller, right? If you have a big capacitor, it's a big time constant. You have a big inductor, it's a big time. So there will be a limit on the physical system. So just because the control, you try to increase your proportional gain in the controller. Fine, you have a Toyota, and then the other guy has a Lamborghini. It's independent of the driver, right? So you put the worst driver in the Lamborghini, that's the controller. Put the best driver in the Corolla. You still, I mean, there's a physical system limitation. Here, it's in power converters, it's the L's and C size. That's the limitation. Small L and small c, very dynamic. You can change things very quickly, right? Charge, discharge quickly, do stuff quickly, right? Like a Lamborghini, right? So, good analogy. Okay, so now let's do the buck boost. So everybody's okay with the boost now? Buck, and we did the buck, and now the boost. Then the buck boost, very similar process. I mean, we identify the terminals, passive, active. So this is V input, and this is my switch, and then diode, and output capacitor, resistor, blah blah blah. Again, this is which terminal? Active terminal, and then this is my common, and this is my passive terminal. So you can take this, substitute the two sources that we looked at, and redraw the circuit. So I can redraw the circuit. Next to the active terminal, I have the current source, and then passive terminal, I'll have the voltage source. So this is V input. This is your active, common, passive terminal. This is D times IC, which will also be equal to D times IL, right? In this case, remember what was the polarity? The positive polarity for IC was it was coming out of node C, right? So this was IC, right? This was the positive terminology that we had here. Current is coming out of IC, right? So that was IC current coming out of it. So here, this is my terminal C, current is coming out of it. That current is called IC. It also happens to be IL, so this is in the same. So DIL is equal to DIC, not like the boost converter where we had a flipped problem. And then this is D times VAP, and the polarity will be like this. Again, if you want to confirm what we're doing is correct or wrong, we put a short circuit for the inductor, right? If you put a short circuit for the inductor, what does the circuit look like? It doesn't. I don't care what's on the left because I have a short circuit here, and I don't need to put a capacitor because it's a steady state, right? I'm doing my steady state solution to figure out if my voltage transfer for my boost converter is correct or not. So this is D times VAP, and this is still terminal P, and this is terminal C. Fine, I can put okay. This is my V output. So what does V output equal? Exactly. No. This is a short circuit. So if you take this loop, this voltage plus this voltage is equal to 0. So V output is equal to minus d VAP, right? D times VAP. What is VAP? What is the voltage VAP? The A is here. What's the voltage VAP? In the buck, it was the input voltage. In the boost, it was minus the output voltage. How about here? Exactly. It's the Vin minus V out. So V output is equal to minus D times Vin minus V out. Right? Yes. So I bring V out. So this is minus D V in plus D V out. I bring the V out on one side. So this is V out 1 minus D equals minus D times V in. So V out is equal to minus D over 1 minus D V in. If you go back to the buck boost converter, slide, of course in continuous mode, then here, buck boost, here. It's minus D over 1 minus D times V in. Right, so it's minus D over 1 minus D times V in. Minus D over 1 minus D times V in. Right, so it confirms that our model is correct. Right, so and this model here now you can take and perform 420 material on for L and C. Right? One more note before we wrap up this chapter here. So in all these converters we put one L and one C. That's fine. Let me look at the let's look at the buck converter again. Okay. Why did we put the L and C here? Why do we put the L and C?
To maintain less ripple for
Exactly, because we wanted to create an output voltage with very low ripple. So the way to do that was fine. We said that initially we didn't have this diode. Remember? Initially we didn't have this diode at all. We had a switch and an output resistor. And we said we'll open and close the switch. But then we said that, okay, this will make output current discontinuous. So how do I make output current continuous? I put an inductor. So if I put an inductor there and I open the switch, I will have very high voltage across the switch. That doesn't work. So I have to put a diode. So we created the buck converter that way. So, and when we saw that the inductor current had ripple. This ripple was going to affect the output voltage, because let's say there's no capacitor. If we only have an inductor, initially we only had an inductor, right? We had an inductor because we wanted to maintain the output current continuous, right? And then we said, okay, because I have an inductor, I have to put a diode, right? And then now that I have a switch, diode, and inductor, this inductor will have ripple current, depending on the size of the inductor. So this ripple current, if ripple current flows through the output load, what will the output voltage look like? Same ripple that the inductor has. So how do I mitigate that or reduce that? I add a capacitor. I have output voltage ripple. I want to reduce that, so I put the capacitor. Right. So the same thing applies to the input. By the way, here this is a battery. This is a battery, right? What does the current here look like? What does this I switch look like? When the switch is on, it's inductor current. Switch is off, it's 0. Inductor current, 0. Inductor current, 0. Again, do batteries like to be treated that way? No. Batteries are an average power source. They like to provide nice, pure DC current. Otherwise, you're eating from their lifetime, right? So, because then you're treating the battery as a transient source, because this is not DC anymore. The battery will then be modeled as an impedance in series with a DC source. And here you will have an effect of the inductance of the wires, and it's a bigger mess, right? So which will affect your transient response. So batteries don't like that. And batteries don't like, and their lifetime will be reduced if you do it this way. So how do you treat this? This is causing what? Again, this is, if we look at this current, it's causing, if you consider some inductance here, some resistance here, or some impedance, what is this going to cause to the voltage at the input? No, it will have ripple. It will also have ripple. Because what is the voltage here? This is V input now. This is V prime. What does the V prime look like? V prime will look like your ideal input, V input, which is the ideal voltage source, plus ripple current multiplied by this impedance. So it will look like this. Or it will go to 0. No. Let me just draw this, right? It should just, it should be at the same line as it's the input voltage, the ideal source, plus this drop. This drop, when the current is 0, right? When there is a drop across the impedance, there's a drop, right? So this will be your input voltage. Is this what we used to design the rest of the converter circuit? Or did we assume that inductor, when the switch is off, switch is on, the inductor has what? V input, which is a DC, minus V output, which is also a DC. So inductor voltage looked like this when the switch was on. Now it's going to look like what? When the switch is on, it will look like this, maybe higher. And then when the switch is off, no, this is higher voltage. Huh? It's a different voltage. It's not. This was V input minus V output. It's now V input plus a drop minus V output. Right? So here it was minus V output. Right? Minus V output part will not change. But this changed. So for the same duty cycle, the area on top will not equal the area on the bottom anymore. Right? That's one thing. The other thing is it will cause additional ripple. So since the areas are not the same, you're operating this in transient now. So if you're operating this in a transient, you're not operating this properly. It's not steady state operation of the inductor anymore, which means that the equation that we talked about cannot apply anymore. Right? So how do you solve this? This is what? This is a voltage ripple. Exactly. So since this is voltage ripple, like I had here, I had voltage ripple. How do I treat voltage ripple? I add a capacitor. If I add a capacitor at the input, then what happens? Then this still remains as switch current. Will this change? Switch current will never change. But this switch current now, is it an AC component? Or is it a DC component? Or does it have bits and pieces of both? What is this? This is AC or DC? This is AC plus DC. Right? It has an average value and it has harmonics. So it's an AC plus a DC. Right? So this current here is an AC plus DC value. If I put a capacitor here, then any current flowing through the switch, which will eventually come back through my circuit, right, will have to do what? Will flow through the capacitor. Assuming an ideally large capacitor. Which means that all the AC current will come through this capacitor and allow me to do what? Allow me to bring in nice average battery current from here. Right? So the average value of this current will now be your battery current. This is this. This is I battery. How about capacitor current? Capacitor current will be this current minus the average value. Same thing that we used for designing the capacitor at the output. Right? This is now the IC here. This is capacitor current at the input. Right? So any capacitor, output or input, is designed the same way. As long as it's always treating the same phenomena. There's a voltage ripple problem that you have an issue with. And if you put a capacitor, it will absorb all the ripple current flowing through there and allow that capacitor to maintain a fixed voltage, or a voltage with less ripple. you want to call it. So capacitors at the input or output are the same. Do you see why we added one here? Right? It wasn't clear. I mean, I didn't explain too much before, but this is. I hope it's clear now. So this brings me to the end of this chapter. So hopefully you have a good idea. So this is the last thing that we talked about. So I talked about a lot of stuff in this chapter that is not in the textbook. Okay, like the losses. The details of the control, how do you rate this to 420 is it's not explained in the actually they just put 2 sentences. So if you just read from the textbook, you will not understand anything. So what we went through, we spent a whole day today on just 2 sentences that they put in the textbook. I think it's so important to explain those 2 sentences. That's why I spent a whole lecture on them, because they ties you to 420 and 214 very nicely. So, and this is really the full spectrum of designing a power converter. You select your devices, select your reactive elements, then simulate a switch model, simulate an average model. From that average model, derive the transfer function, and then from 420 material, you should be able to design a controller to figure out the value of duty cycle and how do you change duty cycle to maintain a certain output voltage regardless of load changes, right? All of that within the context of also understanding the efficiency of the converter by talking about the losses, right? So hopefully that tied everything together. I think it's a lot of things to tie at the same time, but this is power electronics, all of this together. So we'll stop here. Next time, I was hoping to start chapter 8, but next time I will record. So in the chapter 8 first lecture, I will record it.
Mm-hmm.
Yeah, I will record the first lecture of chapter 8. It should be easy. And so that will be an introduction chapter 8, and then you will have the exam on Wednesday.
And the quiz on Monday is on the introduction to chapter 8.
Yeah, the quiz on Monday will be the lecture that I will post today, inshallah.